Hello, everyone. I'm Kanishka Misra, a PhD student at Purdue University, and I'm excited to talk about my paper entitled Do Language Models Learn Typicality Judgments from Text? This is work with Alison Ettinger from the University of Chicago and my advisor, Julia Rise from Purdue University. I want to start off by introducing the phenomenon of typicality, which suggests that certain members of a category are more representative to it than others. As an example, according to native English speakers, robins and sparrows are more typical to the bird category than are penguins and flamingos. And this was originally observed by Eleanor Roche in her seminal work in the early 70s. Since then, typicality has often occupied a central role in the study of concepts and categories. It crucially affects performance and patterns observed across several tasks such as sentence verification, exemplar production order, concept acquisition, category-based induction, and many other tasks. Meanwhile, recent advances in natural language processing have led to neural network-based language models that rely on distributional statistics contained in raw texts to learn general-purpose text representations. These models impressively learn a wide variety of patterns related to encyclopedic knowledge, categorical knowledge, and conceptual knowledge. In this work, we ask the question, how much do these statistical associations learned by these sequence learners reflect typicality effects in categories? Specifically, we have evidence that suggests that when explicitly queried, these models learn quite a bit about concepts and their generally known properties. But are they then able to use this information implicitly and then make judgments about the graded status of categories? So to study typicality in language models, we rely on two phenomena where humans process linguistic stimuli and robustly show sensitivities to typicality effects. First, we test language models on the task of taxonomic sentence verification. In this paradigm, subjects were faster at verifying the truth of sentences expressing taxonomic propositions about typical as opposed to atypical items for a category. For example, the truth of a robin is a bird is judged faster by subjects than the truth of an ostrich is a bird. We then complement the sentence verification experiments by also investigating typicality effects in language models on the basis of how they extend new information about items to all members of the category. For this experiment, we rely on category-based induction, where subjects are studied based on how they reason inductively about categories. Inductive reasoning consists of a premise-conclusion setup, where the conclusion does not necessarily follow from the premise. So category-based induction involves the study of how people extend new information about items mentioned in the premise to the entire category, which is mentioned in the conclusion. For example, if people are told that robins and eagles have the T9 hormone, how likely is that all birds have this T9 hormone? And so this is quantified by researchers as the psychological strength of the inductive argument. And therefore, this paradigm sheds light on how people use their prior conceptual knowledge to extend recent evidence about items to all other members of the category. In the context of typicality, subjects are more likely to generalize new information about a member to the entire category when the member is typical to the category. That is, subjects are more likely to believe that all birds have a property when robins have that property than when penguins have that property. A caveat here is that these properties are supposed to be blank. That is, the agent should have minimal information about the property. So to summarize, through the taxonomic sentence verification experiment, we ask a simple question of whether language models capture typicality while attributing items to their superordinate categories. While through the category-based induction experiments, we aim to ask a more complex question that targets the use of concept typicality in making inductive leaps that go beyond the available data. Using these two phenomena, we study recently developed transformer-based language models that come in two variants. Masked language models that use bidirectional information to fill in the masked word in the input, and incremental language models that predict the conditional probability of a word given a sequence of preceding tokens. We study 4 different families of masked language models and 1 family in the incremental language model variant. In total, we study 19 different neural network language models, all based on the transformer architecture. And while we only study the transformers due to the precedence in the study of conceptual knowledge, our methods can be applied to any language model. But as a baseline, we also include a 5-gram language model that is trained on Wikipedia to investigate typicality effects that is attributed to more simplest statistical learners as opposed to these more distributed representations that arise in these neural network-based language models. So we use typicality ratings collected by the original Ross study, where native English speakers were tasked to rate the goodness of example for 565 different items across 10 categories. We use this data as our general ground truth typicality evidence in both our experiments. So we create templates representing the stimuli that were used in the original papers for our two phenomena, and then plug in the items and categories that we derive from the original Ross study. For the taxonomic sentence verification paradigm, we have 565 different sentences expressing category memberships across 10 categories, leading to examples such as a robin is a bird, an ostrich is a bird, or a hammer is a tool, etc. For the category-based induction paradigm, we first create blank properties such as can Dax, is Vorpal, are Mimsy, etc., using nonce words that are not present in the model's vocabularies, so as to be compliant with the blank property condition and criteria that were mentioned in the previous papers. And so using these nonce words together with the 565 different items and categories, we come up with 12,000 different premise conclusion pairs, leading to examples such as robins can dax, all birds can dax, hammers are slithy, all tools are slithy. Following precedence, we primarily use log probabilities for words in context computed by our language models as the main variable of study of interest. As an example, for the taxonomic sentence verification experiments, we compute the log probability of bird given the prompt an ostrich is a. And for the category-based induction experiment, we compute the log probability of the conclusion given the premise, and use this as the proxy of the model's interpretation of the strength of the inductive argument, that is, how likely is the conclusion given the premise. In each of the computations of these measures, we vary the item for each category and keep everything else as constant. I'm happy to talk about the crucial details that led to these decisions during the Q&A. Let us now take a look at the results. In the taxonomic sentence verification experiments, we measured the correlation between human ratings of typicality and the probability of assigning items to the category members. So we find largely positive but modest correlations across all our models, with GPT-2XL, which is the largest of the lot, to show the greatest correlation. Interestingly, the 5-gram language model is competitive with many highly expressive language models, suggesting that a considerable amount of typicality effects in these models can be explained by simpler statistical mechanisms as opposed to more complex distributed representations. We further divide the set of items into high and low typical categories using a median split on the original data conducted by Roche, and find that language models qualitatively mimic humans in rating highly typical items with greater scores as opposed to low typical items. However, they are less extreme in this behavior as compared to humans. Next, we move on to our category-based induction experiments. The goal of this experiment is to use log probabilities of generating the conclusion given the premise as a proxy for the argument score of the induction as interpreted by the model. This method presents several unintuitive heuristics that the model might rely on and which could confound our measures. Specifically, the model might not compositionally be processing the premise and instead generating the conclusion either due to the overlap or due to co-occurrence statistics relations between the premise category and the conclusion. So to alleviate this potential problem, we identify two confounds. First, we identify this confound known as premise order sensitivity, which computes the log probability of the conclusion given a jumbled version of the premise. So here the model should not be able to compositionally process the premise to generate the conclusion. In our next confound, the taxonomic sensitivity confound, We compute the log probability of the conclusion given a manipulated version of the premise. And so here the taxonomic relationship between category and the item in the premise and conclusion is violated. So we fit a model to predict our original argument strength scores in the language models using these confounds. And we found that these confounds explain about 43% of the variance in our original argument strength scores. We therefore use an adjusted version of the argument strength scores by regressing out these confounds. We again compute the Spearman's correlations between the ground truth typicality ratings and our adjusted AS scores and find, similarly to the previous experiment, that inductive tendencies in language models only moderately correlate with human typicality judgments. Note that the 5-gram language model is absent here, since our stimuli examples are all longer than the context that can be captured by the 5-gram language model, and therefore it produces constant probability scores regardless of when the premise is changed. We also notice that larger and more expressive language models generally tend to show better performance or better correspondence with human typicality ratings in the taxonomic sentence verification paradigm, but substantially less so in the category-based induction experiments. This suggests interesting implications for model scaling and categorical knowledge, which we leave for future work. In summary, word prediction capacities in language models show modest correlations with human typicality judgments, suggesting that these models might miss out on the fine-grained graded categorical information during pre-training. And this is seen both in tests targeting taxonomic sentence verification and argument strength patterns in category-based induction as conducted on these models. However, in both setups, we do find that LMs are qualitatively similar to humans in distinguishing high and low typicality items, but their behavior in this aspect is less extreme as compared to humans. So while it is impressive that these models do capture commonly known properties of concepts, our results suggest that they're unable to reliably use them to reflect complex categorical structure, which is largely graded in nature as found in much of research in cognitive science. We speculate that this might be the case because real-world texts rarely mention obvious facts about the world and instead have a bias to report the more atypical events and items. And even evidence from recent inquiries suggests that this also propagates to models that are trained to reflect distributional statistics. So future work can aim to correct for distorted frequencies of atypical events and items mentioned in text by informing models from a more grounded source of knowledge. And so one way of doing so could be to explicitly teach language models to learn features of concepts through text so that they are compliant with the feature-based hypotheses of typicality. And we hope that this opens up new possibilities in the study of these models' synthetic semantic cognition. Thanks for your attention, and I will see you at the Q&A session.